In this example, we're going to use the equation of continuity as well as Bernoulli's equation to solve the following problem. Let's suppose that water is circulating through a continuous solid pipe in a house. If the water is pumped at a velocity of 0.6 meters per second through a diameter of 10 centimeters in the basement under a pressure of 3.039 times 10 to the 5 newtons per meter squared, what is the flow speed and pressure in a 4 centimeter diameter pipe 6 meters above pipe number 1, above the pipe in the basement? So let's suppose we have the following continuous pipe and we label this pipe section as pipe section number 1 and this pipe section as pipe section number 2. Now the cross-sectional area of our pipe in the basement is given by A1 and the cross-sectional area of our pipe 6 meters above the basement pipe section is A2. The velocity, the flow speed of our fluid in this section is V1. And the flow speed, our velocity of the fluid 6 meters above the basement is V2. So in the first step, we're going to use our equation of continuity to solve for our velocity V2. In other words, to find the actual pressure 6 meters above the ground, above the basement, we first have to calculate the flow speed velocity V2. So to calculate velocity V2, we have to use our equation of continuity, which basically states that the volume flow rate at any given point in our continuous pipe is exactly the same. So the volume flow rate in this section of the pipe, A1 times V1, is equal to the volume flow rate in section number 2, 6 meters above the ground, A2 times V2. Now, we know what A1 is and A2, and we know what V1 is. So we can solve this equation for V2. V2, our velocity of the fluid 6 meters above our basement, is given by the product of the cross-sectional area of section 1 multiplied by the velocity of the fluid in section 1 divided by our cross-sectional area of the pipe 6 meters above the ground in section 2. So, the cross-sectional area of section 1 of this section is simply pi times the radius squared. Now our diameter is 10 centimeters, that means the radius is 5 centimeters, and to get the meters we simply divide by 100 and we get 0.05 meters squared times pi multiplied by velocity V1, the velocity in section 1 of the pipe, and that's 0.6 meters per second. So we divide that by the area, by the cross-sectional area in section 2 of the pipe 6 meters above our basement. So pi multiplied by, well, we know our diameter is 4 centimeters, so we divide this by 2. We get 2 centimeters as the radius and divide that by 100 to obtain our radius in meters. So 0.02 meters squared multiplied by pi, and we get 3.75 meters per second is our velocity of the fluid in the section of the pipe 6 meters above our basement. Now, in part 2, we want to use this flow speed V2 to calculate the actual pressure in our pipe 6 meters above the basement level. So, here we need to use Bernoulli's equation. So, Bernoulli's equation basically states that the pressure at point 1 in the basement within the pipe plus our pressure due to the velocity of our fluid in that section of the pipe in the basement is equal to the pressure 6 meters above the ground in the pipe, this is what we're looking for, plus the pressure due to the velocity of the fluid in this section, plus our difference in pressure due to our change in height when we go from this level to this level 6 meters above the ground. So, since we want to calculate pressure 2, the pressure at point 2, we have to solve for this quantity. So P2 is equal to Well, we have P1 plus this quantity minus this quantity and minus this quantity. And we get the following result. Now, let's actually plug in our values. So we know P1 is 3.039 times 10 to the 5 newtons per meter squared, which is 3 atmospheres of pressure, plus 1/2 our density of the fluid, and since we assume it's water, the density is simply 1,000 kilograms per meter cubed. Now, our V1 squared is simply 0.6 meters per second squared. Our V1 is the velocity in the basement section of the pipe, minus 1/2 times our density 1,000 multiplied by 3.75 meters squared, which is our velocity of the fluid in the second section of the pipe, 6 meters above the ground, above the basement, minus 1,000 kilograms per meter squared, our density of water, multiplied by G, our gravitational constant, multiplied by the change in vertical distance between the basement section of the pipe and this section of the pipe, which is simply 6 meters. So we plug our values into the calculator and we get a pressure of 2.38 times 10 to the 5 newtons per meter squared, which is approximately equal to 2.35 atmospheric pressure. So notice that this pressure is slightly less than the pressure in the basement, and that's because the velocity in this section is higher. Recall what Bernoulli's equation states. Bernoulli's equation states that in the place where you have a greater velocity, you have a smaller pressure. And in the place where you have a smaller velocity, you have a greater pressure. So that means here our pressure will be greater and here our pressure will be less because the velocity here is greater than the velocity here. And that's exactly why P1 is greater than P2.